So we will be solving two questions today on circular motion and gravitation. So the first question here is from October-November 2010, question paper 43. So there's a planet of mass m that is in a circular orbit of radius r about the sun of mass m, as illustrated in figure 1.1. So we've got the sun here, that is the central body, and this planet of mass m goes around the sun. R here is the distance between the sun and the mass m. The first part of the question says, state what is meant by angular velocity. Now, angular velocity is basically rate of change of angular displacement, rate of change of angular displacement for an object in circular motion. That is angular displacement. Now, part B of the question says, state the relationship between omega and t. What's the relationship between omega and t? We know that omega is equals to 2 pi upon t, or omega is inversely related to t. Inversely related to t. We can also write the relationship here, that is, the relationship is omega is inversely related to the time period. Part B of the question says, show that for a planet in circular orbit of radius r, the period t of the orbit is given by the expression t squared is equals to c r cubed. So we need to prove this relationship between the time period of an object in circular motion and the distance or the radius r. Now, to start off with this relationship, we need to first understand that in this case, the centripetal force Fc is provided by the gravitational force of attraction. Fc is equals to Fg, or Fc can be written as mr omega squared is equals to gmm over r squared. Now, what do we need in this relationship? The final answer requires us to include time period and radius r. The only way we can get time period here is by substituting omega as 2 pi upon t in the equation. Since time period and radius here is in the numerator and we've got the constant with the radius, what I'll do is I'll shift this entire thing to the other side and I'll shift time period onto the other side of the equation. This will give me m r cube 4 pi squared upon g m m is equals to time period square. This mass here, the lowercase m here, cancels out with this lowercase m, and we get the equation as r cube 4 pi squared upon gm, which is equals to t squared. This entire thing is the constant c. So r cube c is equals to t squared. Moving on to the next part of the question, part C says, data for the planets Venus and Neptune are given in figure 1.2. We've got the radius of Venus, that is 1.08 into 10 to the power 8 kilometers. Don't forget this 10 to the power 8. Don't ignore this. Students often tend to miss this out. And this here is in kilometers. And the time period for Venus is 0.615 years. The time period for Neptune here is missing. The question says, assume that the orbits of both planets are circular. Use the expression in B to calculate the value of t for Neptune. Now you can use this expression t square is equal to cr cube in multiple ways. You can either say t squared is equals to cr cube. You can either find out the value of c using the radius of Venus and the time period for Venus, and then use that value of C with the radius of Neptune to get the time period of Neptune. Or the other way of solving this is by using ratios. Now, since C here is a constant, T squared is directly proportional to R cubed. The time period for Venus is 0.615. Don't forget this here is in years. And the radius is, this is squared, and the radius is 1.08. Don't forget this here is into 10 to the power 8 kilometers. The reason I'm not writing 10 to the power 8 and kilometers is because this will cancel out eventually. The time period for Neptune is the time period of Neptune is unknown, squared, and the radius for Neptune is 45 into 10 to the power 8 kilometers. Once again, the reason I'm not writing 10 to the power 8 and kilometers is because this will eventually cancel out. I can now cross multiply to find out the value of time. The value of time period comes out to be 165. Now, since my original value of time period here, this is in years, this value of time period will also be in years, so 165 years. If the question instead wanted me to give the answer in seconds, I could have converted this here in seconds to get the answer in seconds, or I can multiply this 165 by the constant to get the answer in seconds. Moving on to the next part of the question. The next part of the question says determine the linear speed of Venus in its orbit. Now, we've got the time period for Venus, that is 0.615. We've got the distance or the radius for Venus, that is 1.08 into 10 to the power 8 kilometers. Let's copy that down. So, for Venus, the time period is 0.615 years, and for Venus, the radius or the distance from the Sun is 1.08 into 10 to the power 8 kilometers. Now let's have a look at the units given in the question. The final speed that they want is in kilometers per second. So I know one thing for sure. I can keep this value of radius in kilometers, but I'll have to convert this time period in seconds. Before that, let's figure out the formula that we'll use. The formula for linear speed or tangential velocity is V is equals to R omega. V is equals to R. Radius in kilometers is 1.08 into 10 to the power 8 kilometers. Omega is 2 pi upon capital T, with that is the time period. So if you've got 0.615, but this is in years, we've got 365 days in a year multiplied by 24 hours in one day multiplied by 3600 to get the answer in seconds. This will give us a value for velocity as 35 kilometers per second. This here is the solution to the first question. The second question that we'll solve today is from October-November 2012, paper 41. The first part of the question says state Newton's law of gravitation. Now, Newton's law of gravitation states that for any two point masses. Now, point masses is the important terminology here. Newton's law of gravitation is only applicable for point masses. For any two point masses, the force of attraction is directly proportional to the product of the masses, and inversely proportional to the square of their separation. This is what Newton's law of gravitation says. F is equals to gmm upon r squared. Part B of the question, it says a satellite of mass m is in a circular orbit of radius r about a planet of mass m. So we've got a central planet m, and there's a satellite that goes around that planet m. For this planet, the product of gm, so they've given us the product of g and the mass of the planet, is 4.0 into 10 to the power 14 Newton meter square per kilogram, where g is the gravitational constant. The planet may be assumed to be isolated in space. By considering the gravitational force on the satellite and the centripetal force, show that the kinetic energy Ek of the satellite is given by the expression. So we know that for this satellite in circular motion, the centripetal force is provided by the gravitational force of attraction. So this is where we'll start off. Fc, the centripetal force, is provided by the gravitational force of attraction. The equation of centripetal force is mv squared upon r, which is equals to Fg, that is g m upon r squared. Now we want Ek on one side of the equation. We want kinetic energy on this side of the equation. The formula for kinetic energy is half mv squared. Let's write that down here. Ek is half mv squared. So if we can get half mv squared on this side of the equation, I can replace that with Ek, or kinetic energy. What I'll do is I'll multiply this r, or shift this r to the other side, or multiply r to both sides of the equation. That will have the same effect. And I'll also multiply half to both sides of the equations. This gives me half mv squared is equals to half gmm upon r. This r here cancels out with this square. Now I can replace this half mv squared with Ek is equals to gmm upon 2r. So we've proved the expression. B part 2 says the satellite has mass 620 kg and is initially in a circular orbit of radius 7.34 into 10 to the power 6 meters. Resistive forces cause the satellite to move into a new orbit of radius 7.3 into 10 to the power 6 meters. Determine for the satellite the change in kinetic energy. That is the first part to part 2. So initially this was the position of the satellite. Resistive forces caused the satellite to change its radius, and now it's closer to the planet. We need to find the change in kinetic energy. So what we'll do here is we'll use the formula that we derived in the previous part. So Ek, as we all know, is gmm upon 2r. So we'll find the kinetic energy at the two different values of radiuses. We can do that directly, or we can break it up and then do it. So if you do it directly, we'll get Ek is equal to gm. This product of g and m as given in the question is 4.0 into 10 to the power 14. So I'll replace these two with 4.0 into 10 to the power 14. This mass here, the mass of the satellite as given in the question, is 620 kilograms into 620 upon 2 multiplied by the two radiuses, the difference between the two radiuses, 1 upon the final radius, that is 7.3 into 10 to the power 6 minus 1 upon 7.34 into 10 to the power 6. 7.34 into 10 to the power 6. Now, what some students tend to do is they write it like this. 1 upon 7.3 into 10 to the power 6 minus 7.34 into 10 to the power 6. This is incorrect. You'll get an incorrect answer using this. So if you are confused, instead of writing it as one equation, solve it separately. Find the kinetic energy at the old radius, using the old radius, and the kinetic energy using the new radius separately, and then subtract the two. This will give me a value of approximately 9.26 into 10 to the power 7 joules. Part 2 of the question says gravitational potential energy. So they want us to determine for the satellite the change in gravitational potential energy. Now the change in the formula for gravitational potential energy is Gmm upon R. EP is Gmm upon R. Similar to the previous part, you can either solve it separately, find the potential energy using the old radius and the new radius separately and then subtract the two, or form one equation. This Gm is 4 into 10 to the power 14 multiplied by mass of the satellite, that is 620, multiplied by 1 upon 7.3 into 10 to the power 6 minus 1 upon 7.34 into 10 to the power 6. This will give me a value of approximately 1.85 into 10 to the power 8 joules. The last part of the question says use your answers in 2 to explain whether the linear speed of the satellite increases, decreases, or remains unchanged when the radius of the orbit decreases. Now the linear change of the satellite has to do with the kinetic energy. If you have a look here, this is the final kinetic energy, this part here. And if you use this fraction with these, you'll get the initial kinetic energy. So if you have done this separately, you'll notice that the final kinetic energy is greater than the initial kinetic energy. Or if you've done this like this, you'll notice that this answer here is positive, which means that there's an increase in kinetic energy, which automatically means that the linear speed increases. So I'll write that Ek increases. Hence, we can say that speed has increased. Or you can say that the change in kinetic energy is positive, which means that the speed has increased.